Now we are going to discuss this question number 6.4, and in this question it is given to you a rectangular wire loop of side 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. Clear? So let us try to understand this situation. Let's suppose I am taking here, actually here we have two sides, so let's suppose I am drawing here. Clear? Let's suppose this is a rectangular wire, it is given to you, and here we have a small cut. Clear? Small cut means we can say here this loop is not a closed loop, this one is open. Clear? In this question it is given a rectangular loop having side 8 cm. I can say this one is 8 cm. Clear? And this is given to you, this is 2 cm. Clear? This one is 2 cm with a small cut is moving out of a region of uniform magnetic field. Clear? Uniform magnetic field of magnitude. So let's suppose I am assuming here magnetic field is in this direction. This is uniform magnetic field. Now listen carefully. So you can assume this black one is a uniform magnetic field that is perpendicular inward direction. Clear? I can say here if we talk about this question, what is EMF developed across the cut if the velocity of a loop is 1 meter per second in a direction normal to longer side. So first, if I am talking about part number A, let's suppose I am assuming this loop, or we can say this actually rectangular wire loop, it is moving in an upward direction, or we can say it is perpendicular to this longer side. Clear? Definitely actually we have a one concept, when a current carrying wire is actually moving in a magnetic field, at the time an induced EMF will be developed. Induced EMF will be developed through this across this end. Clear? So what about the magnitude? Listen carefully. Velocity is given to you in this direction. Clear? I can say this longer side it is given that is perpendicular to this velocity, and you can also observe here magnetic field, velocity vector and this length all are mutually perpendicular to Clear? So definitely you know here one formula, when B, I can say B, BVL all are perpendicular to each other, at the time you can write like this, induced EMF is given by BVL. Clear? So value of B we have that is 0.3. Clear? Velocity is given 1 centimeter per second. I can say this is 10 to the power minus 2 meter per second. What about length? Clear? Length is given to you 8 centimeter. So 8 into 10 to the power minus 2. Clear? So from here we can see this is given by 8 multiply 1, and this is 0.3, so 2.4 into 10 to the power minus 4 volt. Clear? So this is induced EMF when the longer side, when we can say this velocity is acting perpendicular to this longer side. Clear? So this is case number 1. Now let's suppose if I am talking about part number B. Clear? Or in part number B, actually this velocity vector or velocity is acting on a shorter side of a loop. So let's suppose in second case I am saying, let's suppose velocity is in this direction. Clear? Now again you can see here velocity, if I am talking about this distance, that is B, so V, B and capital B. Clear? Or you can say let's suppose this is yes, V, capital B or this small b, all are perpendicular to each other. Again you can apply here we can say this formula E, it is given by B, V, L. Clear? L, instead of L I will write this is B. Clear? So value of B, this is given 0.3. What about velocity? Velocity is same, 1 centimeter per second, so 10 to the power minus 2. And what about this side? Side is given 2 centimeter, so 2 into 10 to the power minus 2. Clear? So from here we can say this is equal to 2 multiply this one, so 0.6 into 10 to the power minus 4 volt. Clear to everyone? So this is induced EMF that is developed across this end. Clear to everyone? Actually you can find also the direction of induced EMF. Clear? So now we can say actually here we have one more part, for how long does the induced voltage last in each case. So actually induced voltage will be developed across its end till we can say magnetic flux will change, clear, or there is a whenever this current carrying loop, or we can say this rectangular loop that remains in a magnetic field, clear. So now we can say, can we find here total time taken in each case? Yes, I can say total time taken in first case, clear. If I find here total time in first case t, this is given by, now I can say what is distance covered. So when this loop is going in this direction, distance covered in this magnetic field is only 2 centimeter. I can say that is distance covered about, and velocity. Velocity is given 1 centimeter per second. So I can say total time taken is 2 seconds. Clear in case number 1. What about total time taken in case number B? Clear. I can say in case number B, total time is what? Total distance covered in the magnetic field, this is 8 centimeter. So 8 divide by, we can say what about velocity, this is 1, so this one, clear. So from here you can say this is 8 seconds, clear. So like this we can calculate here total time also, clear. Okay, so this is all about discussion.